Now we have learned what a time series is. We know what a time series looks like. Next thing to learn would be what are the various components of a time series. We are going to take a time series and dissect it and look at the various components. And to start with, the various components of a time series are the trend component, the seasonality, and we have already had a brief look at seasonality when we were looking at eBay sales data. So seasonality is the fact that sales data goes up from the months of October through December. And the third component of a time series are the random fluctuations. And we are going to see what each one of these mean. Now, again, as I have already mentioned, why do we need to dissect a time series? We need to slice up a time series into the various components because the forecasting algorithms, it depends on which forecasting algorithm we are going to choose depending on which components are present or absent in the time series. Now, since we're going to use R, you can use R to dissect a time series, invoke certain commands in R, and slice up a time series into its various components. And this is the output that you get when you dissect a time series using R. Now, the top panel in this output is the original time series, the eBay sales data time series that we have already seen. So the top part is the eBay sales over various years. And the remaining three panels shows the three trends the three components that we have just learned about. The second panel is the trend component. The third panel shows the seasonal component, and the last panel shows the random fluctuations in the sales data at eBay. So what is the trend component? The trend component is the overall long-term pattern that lies in the data. So you're all familiar with trend lines. Maybe if you input some data in Excel and ask Excel to draw a trend line, it will show you a trend line. So this trend component is similar to the trend line of any data distribution. The seasonal component shows you the systematic periodic fluctuation that repeats at certain specific time points, say at certain months of the year or certain seasons, certain parts of the day, etc., etc. So seasonality is the periodic fluctuation which repeats over time. The random component, unlike the other two components, the random component cannot be fit into any pattern. So it is the irregular component. And all three of those added up makes up our observed time series. Now, some of the time series may have all of these components. It may have the trend, seasonal, and random components. Some might not. So in this slide, I'm trying to show you on the left, I'm showing a time series which does not have the seasonal or trend component. So you can see the seasonal or the trend component are flat. They're straight lines. While the time series shown on the right side has a seasonal component, it has periodic fluctuations, certain time points, and it also has a trend component. So just be aware that not all time series will have all the three components. They might be lacking either seasonality or they might be lacking both seasonality and trend and might just have the random component. So that said, now that we know that each time series may have three components, trend, seasonality, and the irregular part, there are two kinds of time series, two flavors of time series data that we might come across. We might have an additive time series or we might have a multiplicative time series. Now, these two types of time series depends on how the three different components add up to describe the original time series. And we are going to have a look at it. Now, this is a plot of an additive time series. Now, what do you need to notice in it? This is a time series of rainfall over time. So it is a time series of rainfall collected at the end of each year, consistently, regularly. So it is indeed a time series. Now, what is to be noted in this plot is that the fluctuations across time are roughly constant. The fluctuations do not vary. That is, the data do not fluctuate way more or way less at any time point than the remaining time points. And what that means is that if you take 25 inches of rainfall, that is right here, and draw a straight line across the data, at any time point, the mean of the data is roughly 25 inches per year. So as we progress with time, the mean does not change. And one more term that I would want you to be aware of and we'll be using very frequently is the level of a time series. Now, a level of a time series is the amount of fluctuation as we progress with time. Now, here in an additive time series, as the level of the time series progresses, the fluctuation stays more or less constant. So in very simple words, an additive time series fluctuates the same way across time. It fluctuates the same way as the level of the time series changes. And what does that imply mathematically? Mathematically, that means that all three components of the time series, the trend, seasonality, and the random part of the time series, can simply be added up to describe the original or the observed time series. So an additive time series, as the name implies, is a one in which the components can be added up to describe the observed time series. Now let's have a look at the multiplicative time series. Now this is a time series of monthly job advertisements. Now if you compare this time series with the previous one, with the additive one, here's the additive one and here's the multiplicative one, you definitely do see noticeable differences. And what is the difference? Like as you progress across time, that is, as the level of the time series changes, the fluctuations change. Notice, like here, in the year of 89, like if you look at the fluctuation in the year of 89, the data is dipping right up to here. It's a long dip. And the peak is also pretty high. But if you look at the dip, say in the year around 93, the dip is pretty small. And the peak is also very small. So the dip over here and here are very different. The fluctuation in the data as the level of the time series progresses across time are very different. The data in a multiplicative time series do not fluctuate the same way across time. And because of this, mathematically, the components of a multiplicative time series need to be multiplied. Well, as the name implies, this is a multiplicative time series. So the three components needs to be multiplied to describe the observed time series. For our forecasting algorithms, what we need is an additive time series. All the forecasting algorithms are kind of formulated or written based on the assumption that the time series is additive. And hence, if we have a multiplicative time series in hand, we need to convert it into an additive time series. How do we do that? So, in case of a multiplicative time series, the trend, seasonality, and the random components need to be multiplied. Now, if you just take the log on both sides, the left and the right, the equation looks like this. So now the logs of the component, the log of the trend, the log of the seasonality, and the log of the random component of the time series can actually be added up to describe the log of the observed time series. And hence, bingo, like we have an additive time series instead of multiplicatives. If we come across a multiplicative time series, all we need to do is to log transform the data to get an additive time series. But beware that the moment we take the log, the scale of the data, that is the units of the data, decreases, or definitely you can appreciate the fact that it changes. And we are going to see how that influences our forecasting algorithm, or more precisely how it influences the validation part of a forecasting algorithm.